take this opportunity to thank Indian Academy of Science to talk in the media meeting. So I will be talking on the aerosol radiative forcing over India and regional climate. It is basically I'm leading a project under ISRO on the aerosol radiative forcing estimation. So we all know now, just now we listened to Binita, we are familiar about now the aerosols. And so aerosols, we know these are the particles suspended in the atmosphere. There are basically in terms of climate, its interaction with radiation which makes them important. So it interacts with radiation basically through scattering and absorption, we know. So broadly, as far as I am concerned, aerosols are of two types. Aerosols which scatter radiation and aerosol which absorbs radiation. So we all know that scattering aerosols basically are sulfate, nitrates and organics. But when it comes to absorption, basically it is the black carbon, as the previous talk it was mentioned, and dust also contributes to absorption of radiation. So when we talk about aerosols, aerosol radiative forcing through interaction with, especially with short-wave radiation, it affects the radiation balance of the Earth atmospheric system. So the radiative forcing here is basically the change in the net radiative flux at the top of the atmosphere due to an external perturbation. And in here, it is basically because of the presence of aerosols. So when we talk about positive radiative forcing, means it is warming in the system, and negative radiative forcing leads to basically cooling. But here, when we talk about radiative forcing, we all know that we need to do radiative transfer calculation to estimate the radiative flux at the top of the atmosphere. So here, three important parameters which are important are the most important parameter is the optical depth, columnar optical depth, and the single scattering albedo, which determines whether aerosols scatter or absorbs in the atmosphere, and of course the phase function, which is basically the angular distribution of the scattered intensity. Once we have an idea about these parameters, these properties of the aerosols and the atmospheric conditions and the surface reflectance, we can estimate the direct radiative forcing. So when we talk about aerosol radiative forcing, there are different mechanisms. The most important one, which I have already mentioned, which is the direct radiative forcing, which is basically through scattering and absorption, and which leads to cooling at the surface and in the atmosphere, depending on the type of the aerosol, the cooling at the top of the atmosphere, but always leads to warming in the atmosphere. But two other important forcing mechanisms are through its aerosol cloud interaction. The first indirect effect, where the aerosols, when the amount of aerosols in the atmosphere, when it increases, when there is an increase in the aerosol in the atmosphere for a fixed amount of water vapor, the cloud droplet size decreases, and this leads to brighter clouds. But another second indirect effect where it suppresses the or the rain. So there are two indirect effects. So when we talk about the Indian region, the indirect effect, though we have advanced quite a lot on the understanding on the direct effect of aerosols, but when we talk about the indirect effect, it is in the initial stages probably, because we need to characterize the hygroscopicity of aerosols to have for the better estimation. And another important forcing mechanism is the semi-direct effect, where the absorbing aerosol, because South Asian region especially, the atmosphere contains significant amount of absorbing aerosols like black carbon, which are quite smaller in size range, and when it spends more time in the atmosphere, it interacts with the sulfates and organics, and we call it as aging of the black carbon aerosols, and it becomes more hygroscopic. So it can be part of clouds. It can participate in kind of cloud formation. And when this absorbing aerosol becomes part of the cloud, it interacts with radiation. While interacting with radiation, it can lead to cloud burn and semi-direct effect, which we call. But observational studies on the semi-direct effect over South Asian region is very limited, and there are some attempts now we are making to do that. So when we look at the aerosol map globally, we can see that, basically the aerosols are in the tropical region, mostly when we see. And my talk will be mostly focusing on the South Asian region. So I mentioned that it is as a part of an ISRO program called Aerosol Radiative Forcing over India, where I took a lead role. we have a network of observatories over India. In addition to that, we conduct periodic field experiments using aircrafts and instrumented research vessels. In addition to that, we have space-based observations on aerosols. So combining these three different platforms, we developed aerosol models. We have developed aerosol models over the South Asian region. And this is essential for both for the radiative transfer computation as well as for regional climate model simulation. So now with this information, this is a very good advance in this area of aerosols, that a comprehensive aerosol database and the aerosol model developed, which is now used for the regional radiative forcing estimations and regional climate impact assessment over, focus to different aspects of aerosol climate interaction. And the most important one today, we have some discussion some time back on the aerosol cryosphere interaction, especially over Himalayan region and so on. So in this perspective, we established a network now. We call it as ARFINET, Aerosol Radiative Forcing over India Network. It's a national network of aerosol observatories, and it's mainly operated with the support by ISRO. Here, one of the most important instruments is actually is an in-house developed instrument in our lab, which is basically for the estimation of columnar aerosol optical depth at 10 different wavelengths. It is very important to get spectral values of aerosol optical depth. So all network observatories are equipped with this system. In addition to that, we have observations of black carbon, basically the most light absorbing species in the atmosphere. In fact, now we are operating a chain of observatories along the Himalayan region now to measure the black carbon over the Himalayan region. In addition to that, we have observations on the spectral scattering coefficient to estimate the single scattering albedo and the total aerosol mass and composition from different stations and size distribution, and of course the radiation, because radiation estimation measurements are also important when we talk about aerosol radiative forcing. So with this, now we have a very long-term database. So it's almost spanned for about 3 decades. So first we looked at is actually whether there is any increasing, whether any trend is there in the aerosol. So of course we know that with a lot of anthropogenic activities, which is for the last 3 decades, of course there is the developmental activities. All these contributes to aerosols, these aerosol production in the atmosphere. So if you look at the optical depth long-term trend for the last 3 decades or so, we can see there is an increasing trend. But if you look at the value of the trend, it is of the order of 0.005, which if at a first look, it's a very small number. But when we look in the long-term perspective, it's not so. Because if in a time frame of about 10 to 20 years, the optical depth increase can be of the order of 0.1. In another 40 years or 50 years, it can be of the order of 0.2 to 0.3, which is quite significant, which can reduce the surface reaching solar radiation quite significantly. So as I mentioned before, we have the optical depth measurements at different wavelengths, especially 10 wavelengths. So these spectral observations are very useful to derive the size distribution of aerosols. And when we talk about aerosol size distribution, the smaller particles are basically considered to be from anthropogenic activities, and larger particles are mainly from natural process. So the spectral change, the steepness of the spectral change of columnar optical depth is an indication of the dominance of the smaller particles. Here, the angstrom exponent when we call, which is basically indicate this steepness of the spectral variation of optical depth, this shows an increasing trend. So this increasing of optical depth or aerosol burden over region in South Asian region especially, this is basically is associated with the anthropogenic influence. So we have different stations, but this trend is not same over different region, though I showed it with a simple graph which is averaged over India. It varies with region to region. So when we talk about aerosol trend, unlike carbon dioxide, which is longer lifetime, which stays in the atmosphere for long, the aerosols lifetime is quite small. So as mentioned in the previous talk, even a lockdown for a period of 2 to 3 months can have significant reduction in the amount of aerosols in the atmosphere. But if the activities persist in the atmosphere, for the activities are quite persistent for a long time, the trend can be positive. So This is about the long-term trend. But when we talk about the trend, it is very important to remember one important scientist, Anna Mani, who was very active in academic activities earlier. In fact, she was in the secretary of the academy, I think, sometime in 1970s. She has done extensive work on aerosols in 1960s. She had operated a network of observatories, and which she published in Tellus in 1968, 69 time, two papers in fact. So this was actually the first cut observation on aerosols over Indian region, but due to some reason, probably in 70s, this activity was not very, it didn't sustained or so. So, but this was very useful for me to have a reference about 4 decades back. What was the conditions of turbidity at that time? So I also estimated the turbidity. Turbidity is basically the optical depth at 1 micrometer wavelength. I could see that there is a large increase in optical depth in the last 5 decades. So this is perhaps the oldest data available over Indian region on the turbidity. So there were some observations. Now we have, of course, continuous observations for the climate science community to work on. Now, if we talk about the anthropogenic influence on aerosols, there was a puzzling situation for us now. One of the most in the anthropogenically produced aerosol species is black carbon. There is no natural source for black carbon to be produced in the atmosphere. So if you look at the black carbon concentration, especially at Tumba in the southern peninsula where my lab is situated, the black carbon concentration in the last 2 decades, if you see, it is not showing an increasing trend. Of course, there is large fluctuation, seasonal variation in black carbon, but I can say that it's a slight decreasing trend. But if you look at the absolute magnitude of the black carbon of about 5 to 7 microgram or 5 microgram in the atmosphere, this 75 nanogram in a year is not a big number, but it's not increasing. So the near surface concentration of aerosols, especially the anthropogenic concentration in the last 2 decades, is not showing a very big increase. So then what may be the reason for that? Is it the black carbon is controlled in our atmosphere, and other aerosols like total aerosol system is basically contributed by different species, where the black carbon contribution is about 6 to 10%. Maximum in urban areas it can be 10%, and it reduces to 2 to 3% in rural areas. So whether the black carbon concentration is showing a very steady situation. So another important thing is actually when we look at the Indian scenario and also in a warming world, the convection is increasing. So whether this lighter aerosols like a black carbon is getting transported to the higher altitude, and which is showing a reduction at the surface. So to look into that, I try to look in a 3-dimensional distribution of aerosols over the Indian region. So if you look at for that, basically we have the 3-dimensional distribution of aerosols. There are different ways. One is air measurement is one, but it is quite expensive. So we can have LiDAR. Light means it's light radar impact for laser-based system. LiDARs can be used, but we cannot have LiDARs all over the country. It is quite expensive. So we have to have spaceborne LiDAR. So NASA has operated as spaceborne LiDAR for last 10 years. It's very good. And we have 10 years of data. But here one important issue is actually when we derive aerosol extinction coefficients from LiDAR-based observations, we have to know about the extinction to Basket ratio called LiDAR ratio. So here comes the network is very useful. Here the columnar observations which we made from the network can be used to calibrate the LiDAR observations over India, and we could come out with accurate extinction coefficient profiles. So this is kind of a 3-dimensional distribution of aerosols over South Asian region during different time, like winter when the air mass is basically continental in nature over the Indian region from northeasterly wind. But during the springtime, March, April, and May, the wind gets changed to the northwesterly. So it can take so much of aerosols from the West Asian region. So then that we can see that the springtime when the land gets heated above the Indian region, there is significant amount of pumping of aerosols to the higher altitude compared to the winter. So to find out how much aerosols get transported to the higher altitudes, just I took the difference between the winter to spring. So here I longitudinally averaged the profiles and just took the only the latitudinal variation. We can see that there is during springtime we have an umbrella of kind of the aerosols are situated between 2 to 5 kilometers confined to that area. That means that during the springtime, especially, the aerosols are not getting lost in the atmosphere. If we see, that's what when we see in the Delhi fog and all, we have fog situation during this January and February. When the season changes to March and April, the fog suddenly disappears. It is not due to the aerosol disappearing from the atmosphere, it is getting transferred to the higher altitude. And this is very important. So during northwesterly, this radar is having polarization capability, so I could derive the dust optical depth. So this is during winter time, we can see that the dust influx from the West Asian region is almost negligible. But during the springtime, there is significant amount of dust is getting transported. And if you look at the distribution of three-dimensional distribution of dust, the first, the left graph is basically the integrated backscatter. The rightmost graph shows the dust optical depth. You can see that significant amount of dust is getting transported, especially at a higher altitude. So if you have to get the feel of dust over the Indian region during spring, we have to do airborne measurements, aircraft measurements, which is basically from 1.5 to 4.5 or 5 kilometers, significant amount of dust. So it can definitely, this is during pre-monsoon time, so this can definitely block the radiation which is reaching the surface and thereby affects the radiation balance and hence affect the monsoon climate over this region. So this is one important because the pre-monsoon characterization of aerosols over Indian region is very important. So simultaneously, we have airborne measurements, but to have profiles up to about 10 kilometers or so, we make use of the facility at Hyderabad by Tata Institute of Fundamental Research, TIFR. So this facility, we could profile the aerosols, basically the black carbon aerosols, up to 9 kilometers. So during springtime, you can see that significant amount of black carbon is getting transported to the higher altitude. So simultaneously, we have temperature measurements where the black carbon is high. We could see that there is an enhancement. Temperature is getting there is an enhancement in the atmospheric heating due to aerosols. But if you look at the different species, we can see that over the Indo-Gangetic plain, especially as we go to the higher altitude for different aerosol species, if you look near the surface, it is an organic dominated system. But if you go to the higher altitude, it is basically sulfate dominated. What does it mean? In South Asia, if you look at different aerosol species, it is basically an organic aerosol dominated system. But if you go to the far away from even to the higher altitude, if you go away by research ship over the sea, we can see that as we move away from the continent, it becomes more sulfate dominated. That means the organic is getting evaporative loss. Due to evaporative loss, the dominance gets changed. This also is an important information, and it was useful in our simulation. So I'll just make it a little fast. Now, from this, we could derive the radiative forcing over different regions of the India, and we could find that during the springtime, basically the pre-monsoon time, the atmospheric warming is not dominated by black carbon. It is the dust is the major contributor. So the aerosol radiative forcing, when we talk, even though the winter time black carbon is quite dominant, but when we talk about the pre-monsoon time, which is having more influence on the monsoon climate and because of its influence in the atmospheric warming, we need to work more on the dust aerosols over Indian region, which is not well characterized as far as aerosol system is concerned. There was some discussion about the aerosols over Himalayas. I'm not going into the mechanism, but I would like to, because of the lack of time, but I would like to, our study shows that the deposition of absorbing aerosols decreases the snow albedo over Himalayan region by about 0.15, which is, of course, this is an average value over the Himalayan region. So the statistical uncertainty is quite high. It's about 1.15 plus or minus 0.13, which leads to a positive radiative forcing in the atmosphere about 14 watts per meter square, which translates to a heating of about 1.33 Kelvin. So this is what, based on our observations and the regional climate model, we could derive this, and it is affecting, in fact, the circulation pattern also. So this change in snow cover due to aerosols is mostly contributed by snow albedo effect than the direct radiative effect. Now, before concluding that, I have few seconds. So we have recently conducted the shipborne observations over the oceanic region around the Indian subcontinent. So the research vessel Sagar Kenya was used for that, and it was converted to an aerosol laboratory and had in this study one of the important observations which we could make is actually over the equatorial Indian Ocean. We could make the size distribution of aerosol, which was never made before in the submicron size range from about few nanometers. We could see that over the equatorial Indian Ocean, basically this region, the green shaded region, there are significant amount of new particle formation. So when we talk about aerosol, we always worried about the primary emission. But even for oceanic region, we can have new particle formation from the precursors. So that if the precursor gases get transported from the continent to the oceanic region, or the biogenic emission, in situ emissions over the region, can produce large amount of aerosols in the marine atmosphere. What is the importance of that is simultaneously we had cloud condensation nuclei measurements, means aerosol which act as cloud condensation nuclei. As mentioned before, if there are no clouds in that, no aerosols in the atmosphere, there won't be any cloud. So here we could see that whenever there is new particle formation event, this cloud condensation nucleation efficiency reduces. So this shows that in our marine aerosol system is quite complex. It's not a very simple system, which is quite evident from the single particle measurements which we have conducted to find out how much aerosols is getting aged. Because when the black carbon aerosols spend more time in the atmosphere, the sulfates or organics makes coating and the optical properties of the black carbon aerosols, and hence not only that, the hygroscopic properties and the indirect effect of these aerosols gets affected. So if you look at the coating thickness, it is almost as high as the core thickness of the particles. That means the shell thickness over the existing black carbon is, if it is 100 nanometer black carbon size, the shell thickness is also of the order of 100 nanometer. So that means that when its hygroscopicity increases. So when we had a study, while studying the indirect effect of aerosols using spaceborne observation, we expect that when there is an increase in the amount of aerosols, the cloud effective radius decreases for a fixed liquid water path. But when we changed the liquid water path, means for different scenarios when we looked at, we could see that the cloud effective radius started increasing instead of decreasing, which we expect, which we call it as reversal of the indirect effect. So we could see that over the oceanic region around the Indian subcontinent, probably because of the complex aerosol system, the aerosol indirect effect shows a reversal in the effect. Instead of the cloud effective radius, the reduction, it shows an increasing. This is basically due to the complex aerosol system, like the new particle formation event, as well as the mixing state, needs to be considered to explain this. So I have already crossed the time limit. I'm very sorry for that. I will conclude here. Thank you. I'm ready to take a question. Since I am the last speaker, I have the liberty to take few minutes, I hope. Thank you.
Thank you for that completely fascinating talk. I was just wondering if we could relate your findings to what the first speaker told us in this session. He told us about sizes of drops of the monsoon rain differing between the southwest monsoon and the northeast. And he told us that there were smaller drops in the northeast monsoon compared to the southwest monsoon. And I was just wondering if your findings can somehow integrate with these findings. So do you have a comment on this? Yes, could you please tell us
it
how
is actually,
this is related?
Yeah, it is the cloud droplet radius. We are also now trying to do because in fact we work together on many things, because Dr. Rao, his students are there in my lab, and we are now trying to work out. We started observation on that. But the seasonal change in the cloud droplet effect, the aerosol contribution may not be that significant. But within the season, when there is a change, because the other process, when we say from the southwest monsoon and the northeast monsoon, the system, the process itself is different. where aerosol effect will be on the cloud droplet. The change in the cloud droplet radius may not be very significant. But within the season changes, we can delineate with this, because the other one, the process itself is different, because the cloud system is different. So the type of cloud system involved
yes,
in,
so I was just
in the southwest
wanting,
monsoon as well as in the northeast.
Right, because you also
Yeah.
mentioned about the greater contribution of dust, I think, in the northwest and the, around
Yes.
Rajasthan,
So within the
Delhi.
system,
So
the
is
change
that
can be steady. Yeah, you're right. Yeah,
okay?
you're absolutely
Okay, so
correct. Within this
right.
season, the change in the cloud droplet can be can be associated with the aerosol system. But when the change in during the southwest monsoon, the cloud effective radius and the northeasterly monsoon time, that cannot be connected, because the cloud system itself is different.
Oh, I see. Okay. I think the last question is we often hear about the Southeast Asian, like in Borneo, the fires contributing a lot of
Yeah.
black carbon.
Yes.
So does that
Yeah.
connect, say,
Yes.
if Borneo is burning and it burns every year, how does that connect with our black carbon system?
Yeah. Actually, in the especially over the Bay of Bengal, we could see the effect of Southeast Asian. Basically, you were talking about the Southeast Asian burning, isn't it?
Southeast Asian burning, like in Borneo, for example.
Southeast Asian burning. Yeah. So it is actually, we could see the even there were publications from our lab in about, it was quite some time ago, especially the Indonesian burning. The influence of the Indonesian burning on the reduction over the Bay of Bengal region was reported before. And not only that, we have an observatory for last 20 years in Andaman Island, Port Blair. We could see that there is a seasonally changing air mass pattern is bringing different types of aerosols. And when there is the air mass change shifted to the East Asian region, the influence of biomass burning is quite significant compared to that changes to the Indian region. Because when the air mass is basically from the Indian region, what we found is basically it is dust, mostly of dust, because the particle size is also large. But when it changes to the East Asian region, the particle size also reduces and it is more of produced from the biomass burning. So the effect we could see over the Bay of Bengal. Yeah.
Okay, thank you very much for a very fascinating exposition.